start. So any question from this time? I believe last time we finished this almost the last thing we want to say about density matrix. So in this chapter, I guess in this section, we talk a lot about density operator. So a small review. Once again, we start this density operator or density matrixing, motivated by we want to describe an ensemble of quantum states. And then we see that it's a very general description. We only need to know. So for any n by n matrix that can be described as, it can be describing a density matrix n-dimensional Hilbert space as long as it satisfies those two conditions. So you need to have trace 1 and you need to have PSD. And we can rewrite all quantum mechanics in terms of density matrix. So we postulate, so a quantum state can be written as a density matrix. It's a matrix that satisfying those two conditions. And then when we evaluate in a closed system, then it will evolve according to some unitary, and you get to another density matrix that's U rho U dagger prime. And when you do measurement, basically you got this M rho and M rho and dagger when you get M's random outcome, and the probability is a trace, and you normalize by dividing the probability. And also because we can describe probability example, so we can also have this weird state. That's a post-measurement state without knowing the measurement outcome. And this is some M rho and dagger. And remember this state, a lot of time, in general, rho prime will not equal to rho. Even though you don't know the measurement outcome, you already change the state. And then you have a many system, then you will see then you will have a joint Hilbert space, and then your density matrix is like superposition of density matrix that tensor on each other. Yeah. And then you have equivalent of density matrix. So I guess equivalent of different examples. So example to density matrix mapping is actually many to one. And so many different examples can give you the same density matrix. In particular, this totally mixed state is equal superposition of any two orthogonal state in your two-dimensional space. Okay. And so those are characterization of density matrix. Then we talk about some operations that are related to density matrix. So first is the partial trace. So we talk about reduced density matrix. We're thinking about we have a system that's a larger system that's in some quantum state. So maybe there are two parts, A part and B part, and you are in some quantum state rho AB in density matrix. And we talk about this reduced density. This partial trace operation that give you a reduced density matrix on A. So we are start with possibly entangled state on rho AB, and then we can calculate the density matrix on rho A that will describe everything we want to do on A. So every measurement we want to do on A can be described by this rho A, and obviously you can do evolution on A that will change this rho A. And the partial trace operation is, well, there are multiple definitions. So basically, you want to trace on the B part. So say your density matrix look like this: A1, A2, B1, B2. Then when you do partial trace, then you do trace on B1, B2. Then you get this B2, B1 and inner product, then times. So this is a number, then times the A part. Okay. Yeah. And yeah. So an example is this computational basis. Then you just get delta KO here. And then you can extend this. So this is the product state, but you can extend it to all possible states by knowing that the partial trace is linear. Okay. So you have a linear combination of things, then partial trace is the linear combination of the partial trace. Yeah. So we have some example here, and here we have another formulation of partial trace. You can think of it doing trace on B part, so it's you are sandwiching on whatever you are sandwiching a B part with an orthogonal basis. So we are doing identity on A, then bra on B times identity on A, K on B, and sum over all those I. That's all basis element. That's all the orthogonal basis vectors in B. So that's a reduced matrix that give you from bigger system and get state of bigger system to the density matrix of a smaller system. And here rho AB, so when we define partial trace, rho AB can be pure or can be mixed. But yeah, later we'll see that we want to do partial trace on pure state. Obviously, by definition, this can be mixed state too. And yeah, so as partial trace and reducing matrix, then we talk about 3D decomposition, which is actually about pure state. So it's about entanglement of pure state. So we say that any pure state on system AB can be written in this canonical form. So where it's a summation over sen I, lambda I, and IA tensor MB. So IA is also normal basis that depend on psi AB, and IB is another also normal basis that depend on psi AB. And the important thing here, you are only summing over one I here, so we get only D terms instead of D square terms. Usual D square term like this. Okay. And this can be done by singular value decomposition on the coefficient AJK here. Okay. And we have some example here. Oh, wait, do we not? Oh, I forgot to save. Yeah, anyway. So we have an example here. So very entangled case is you have beta 0, 0, then you have the coefficients lambda I equal to 1 over square root 2, 1 over square root 2 for 0, 0 and 1, 1. And example of another very entangled state is this plus tensor plus. So it looks like 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 with coefficient 1 over 2 on everyone. But when you put it in string decomposition, it's plus tensor plus. And that's just plus tensor plus with the coefficient 1. Sorry. So it's plus tensor plus with coefficient 1, and then also normal part is minus tensor minus with coefficient 0. Okay. So this is actually non-entangled state. And we see that coefficient, streaming coefficient give you some idea about how entangled your state is. So you feel that if it's very concentrated, then your state is very entangled. Is not very entangled, and if it's spread out, it's very entangled. And so there is yeah. And here we use the streaming number as a not very robust way to describe this phenomenon. So streaming number is just the number of non-zero entries in those lambdas. Okay, and then to connect the streaming decomposition back to our density matrix, we talk about this purification operation. So this is operation where you have a density matrix, then you want to find another system and a bigger pure state on bigger system, such that this psi B, when you trace out the R part, it become your rho A. Okay. So basically you want to do a reverse operation of the partial trace. And where this reverse, you reverse to some pure state. So remember, before we have a rho AB can be, rho AR can be a mixed state, but here we want to do something special because we like pure state. And so when we do purification, we go back to pure state. And yeah, and we see this purification has a lot of things, has a lot of connection to the purification. Purification has a lot of things connection to the streaming decomposition. So think about we have some density matrix rho A, then density matrix rho A, then we can purify it to some entangled pure state. And then this entangled pure state, when you partial trace all the reference system, will get back to your density matrix. Okay. And then we see that the eigenvalues of the density matrix here actually correspond to the streaming coefficient here. So if the eigenvalues are pi, the streaming coefficient of your purified state will be square root pi. Okay. So yeah, so we see there is a lot of connection between this entanglement and how the eigenvalues of your density matrix is is distributed. So you see that for as an extreme example, so if the streaming coefficient is very concentrated, then you have a product state between A and R. So it will be like some psi A tensor psi R, and also that makes sense because the corresponding density matrix here will also be a pure state. So if the P here are 1, 0, 0, 0, then you're just summing over some one state, and that's probably your psi A. Okay? And similarly, when it's spread out here, when those PI spread out, the square root PI will be spread out, and that means your density matrix is a mixed state, and the corresponding entangled pure state is, well, it's very entangled. Okay, so that's a 10-minute review. Any question? If not, then let's go to this thing that we actually moved this to previous part, so we know a lot about it already. So it's the Bloch sphere. And so before we talk about this Bloch sphere, so it's XYZ, and they kind of correspond to a physical spin. So it's a way to visualize one qubit, okay? 1 qubit. And we talk about how to make pure state on the surface of this ball. And okay, and so here we still want to talk this again because there is something extra. So we know mixed state, and there is actually something very interesting about mixed state. It's a mixed state mapped to the interior of the ball here. Okay? So we say before the pure state are on the surface of this Bloch sphere. And so for example, 0 is on this z-axis plus, and 1 is on the negative z-axis, and plus is on the positive x-axis, and the minus state is on the negative x-axis. And but there are mixed state, and so mixed state can also be placed here, and it's well, if it's not pure, then it's in the inside of this ball. Okay. And for example, the origin will be the origin will be the totally mixed state, and I guess mixed state. Okay. So here there you have something very fun, very nice here. So mixed state can be described as a linear combination of pure state. Just this is the ensemble interpretation, and actually the ensemble probability will just map to like the vector addition on this ball. And so in more general form, I guess how do I say? Yeah, by definition we so how we map every mixed state to something in the ball is any density matrix we can return as identity plus some linear combination. Every density matrix we can write it as one have identity plus linear combination of polys. And this, so I guess this is also something we need to prove. So this can be proven. Maybe you can do this in a new homework. Okay. Actually, it's probably in a book, so let's not do that. So I can prove that every density matrix can be written in this form. So that's basically because remember in chapter 1 we said that I, x, y, z, so the sigmas and the identity form is a basis for the Hermitian 2x2 matrix, right? Hermitian 2x2. Hermitian 2x2 matrix. And so you can always write your matrix in this linear combination of I, x, y, z. And okay. And so it's positive. So the density matrix is positive, so we know it's Hermitian. And so you can write your rho as a linear combination of I, x, y, z. And then so what's special here is 1 over 2 here, and I believe that comes from this comes from the trace of rho being equal to 1. Okay. So erase this. Okay, so this 1/2 comes from trace rho equal to 1, because the trace of all sigma equal to 0, and So trace row is just this 1/2 plus the trace of identity, and the trace of identity is 2 because it's 2 dimension. So this 1/2 comes from trace row equal to 1, and then we have A here, and so another thing we need to prove is A's are real, right? Those are real, and I believe that come from never mind. A's are real come from just Roy's commission. Okay, and yeah. So you have the A here, and yeah, and then you can do more things to prove that. Okay, so you have the 3A here, X, A, Y, A, Z. So and there are the coordinates on this in this X, Y, Z space, and then you want to prove that A squared is less than 1. And I think this is in homework, I'm not very sure. Yeah, but yeah. So we are trying to say this is inside the ball, and yeah. So this is inside the ball, and that's because A squared is less than equal to 1, and that can be easily proven. I believe that comes from I don't remember if it's in this week homework or next week, but that comes from the trace law square less than equal to 1. Okay. And yeah, so you can get this, I believe. Actually, I'm not very sure. So, trace zero square should be. Anyway, something similar to that. Yeah, but anyway, you can prove that it's actually inside the ball if you write your row in this way, and those coordinates will be inside the ball. And and then you consider you have a linear combination of different density matrix, right? So you have like P1 row 1 plus P2 row 2, and then you will get another. It can be written as another I plus like A3 vector times sigma vector, and so if row 1 has some A1, row 1 has some A1 vector, and row 2 has some A2 vector, and it's easy to see that the A3 will equal to the P1 A1 plus P2 A2, and that's why we say the mixed state. So we see that when you write mixed state as a linear combination of other mixed state, or even pure state, and then the coordinate will just be the corresponding linear combination of coordinate. So we have an example here. So the totally mixed state is in the origin, and we know it's 1/2 of 0 plus 1, and indeed it's in the middle of 0 and 1, and also the totally mixed state here, and okay, so 1/2 identity, and we also say it's plus 1/2 plus and 1/2 minus, and indeed if average length equal to the middle, and it's actually the average of everything that's like opposite of each other. Okay, yeah, and yeah, as we said, the equivalence, uniqueness, etc. can be proved for this thing. Okay, so that's about what we want to say on block sphere mixed state, and I believe other thing we've been talking about, and they have done homework on this. So like the pure state on the every pure state on the sphere can be written as poly in some direction, etc. Okay. Okay, so those we already know, so that's no need to prove them again. And any question? Otherwise, we'll go to a different topic. Okay. So yeah, mixed state. Mixed state is inside the polysphere. It's in the polyball, and they have a really. So I guess we can say a little more. So remember that we say that something doesn't respect the doesn't respect the geometry. So we say the orthogonal of the state doesn't respect the the geometry of the vector space is nothing as the geometry of those polyball. So like two pure state like orthogonal doesn't mean the vectors on the three-dimensional space is orthogonal, but this linear combination or mixed state actually respect the geometry here. So linear combination of 2 points on the polyball will corresponding to the linear combination of the density matrix. So that's something nice to know. Okay, so let's switch gear and because we are behind schedule, so let's try to go really quick. Classical computer science. So this is the first part of the course that we don't know about content. But I think most of you are from ECS, right? So we can go kind of fast here. But anyway, so let's also do some review on computer science. So we build computer science from this most basic concept-based Turing machine. So this is the most idealized version of a computer. Okay. Actually, historically, people think about Turing machine before we actually have computers, okay, modern computers. So it's pretty cool. And anyway, the Turing machine. For now, we can think about one Turing machine is a program or algorithm that want to solve a problem. And so Turing machine has this component. And so it has this head part, and it has program and some basic run here. Okay, so it has a program and finite state control, and then it has a read-write head that I can read on this tape. Oh, sorry, I should talk about it on the tape, from the tape. Okay. And so it starts from you have a tape. So the tape is kind of like a hard disk, and it's infinite long, and you can put depend on the model, and for here we just say we can put 0, 1 and blank here. Okay, so it's infinite long, and there is a read-write head that can read write on your tape, and you can move left and right, and the program will control. The program will see what is the infinite state and what's read on the head, and it will move the head and change the finite state. And so the goal is so it has a really funny input and output model. So tape is both your input and output. Okay, so when you use the program, is usually your head start on some start location, and some input will be written on the head, and the program should do something to change the tape into whatever, to change the things written on the tape into whatever thing it should be on output. Okay. And I think important thing here is about what things are infinite and what things are finite. Okay. And so we say the tape is infinitely long. Okay. And the state control, finite state control is finite. Okay. And so this is kind of like a scaling. So when we solve problem, algorithm should have a finite size, and so you have a finite state control here. It can be maybe a lot of state, maybe like 200, 100, 300, but it should be a finite number that doesn't depend on the input output length. Okay. So that's that. And so let's go to detail of those things. So you have an infinite long tape, and this infinite is really how you scale your things. Your input output can be infinite. And there's a read-write head, and it's kind of a dumb thing. So the read-write part is okay. So you will read or write. So you will read whatever thing here, and then you can write it into whatever thing here. But what's funny here is the movement is really restricted. Okay? So it can move only left and right. Okay? By one step. Okay? So if it's here for now, then the next step it will either move here or stay in the middle, stay at the same place. Okay? And and also you only read whatever symbol here. It doesn't read the position of the tape. Okay? So so it's quite restricted. You don't know where you are on the tape, and you cannot jump to whatever you want on the tape. You can only stay here and then move left and right. Okay. And so this is quite restrictive, but actually the Turing machine is still very powerful. Okay. And as you say, there is a finite state control. So finite means doesn't depend on input-output size. But if you have a more complicated program, you might need more state control here. So is there some memory, and you will say so usually they are labeled as Q. So you have like Q0, Q1, Q2, like Q1, and yeah. So you have a whole bunch of maybe not Q1 because maybe like Q10. Okay. Q10, and yeah. So your program can kind of remember that I am in this state or this state, etc. Okay. And yeah, more complicated program usually they will have more finite state here. Okay. And then there is a program part that actually directs how things should be done. And so as I say, it will read two things. So which state I'm in, okay, so those Q, and what is written on the what do I read on from the head? Okay, so it's a some location. So the read write head is a some collection, and so I will see I'm in some finite state and I read something, and then I will do different things. So one thing special is I will hold, and so the program stop and whatever on the tape is my output, and or then if it's not if the program is still running, then I do many things. Okay. And so I can write down the tape, and so I can do all those at once. Okay. So I can write the tape into whatever symbol I want to write, and then I can change the internal state Q to whatever internal state I want, and then I can also move the head level right, or I guess I can also not move, but that's probably doesn't matter. Okay. So yeah, it's a pretty restrictive model as you see here because say you don't know the head position, etc. But actually you can do, so people have proven that you can do almost every computation you want on this thing. Okay. Okay. And yeah. So here we just go very vaguely, so we can simulate all reasonable computational model. Okay. And for example, your laptop and your smartphone, you can model their function as a Turing machine. And also, something interesting is you can count the Turing machines, because you see the different Turing machines, they are only differ by those two things, right? So like how many finite state control they are, and how the program are written. So here I read it in a better way, but like your program is you can write the instruction set it longer, so it's like what the Q and what the X, and then you change it to so like Q in, X in, then the Q out, X out, and move, right? So the program can be written as those sets, but as you see, all those things are like describable by natural numbers. So yeah. And yeah, so really the number of Turing machines is countable, although there are infinite number of them. Okay. And so if we count them, we can label them and call it Turing number. Okay. That's pretty cool. Okay. And then there is something more like a computer program we can do on Turing machine, and that's the universal Turing machine. Okay. And it's a finite size Turing machine that can do everything other Turing machine do. Okay. So it's pretty funny. We already say there is a countably infinite Turing machine. So how does one fixed size Turing machine do infinite number of things? Okay. So the way we do this is we write a program on our hard disk, like what we do in our computer. Okay. So yeah, this is a really interesting concept. You can do this in universal computation. So yeah, so there is a universal Turing machine. I believe this is what Turing do to get the name on those Turing machines. So you can write the Turing number at the start of your tape, and then you write some blank here and enter input to the problem. And so the universal Turing machine will simulate the Turing machine number Tn. And so this thing will have the computation result that's same as uh, the computation result of the Turing machine N and the computer X. And so yeah, so your universal Turing machine will do what the Turing machine N should do and write the result here and hold. Well, if the N actually hold on X. Okay. And yeah. So to say the Tm is the Turing number for the machine N. So you can write, so the universal Turing machine can simulate every Turing machine in this way. So there is infinite number of Turing number, but so this starting part can be arbitrarily long. And but if you want to run Tm on any Turing machine N, on any Turing machine N, on any input X, then you can just write the Turing number at the start of your tape and the input on the later part of your tape, and the universal Turing machine will write the output on your tape. Okay. So it's really cool. Okay. And yeah, so you see this is kind of like a program. You can write a program on your hard disk. Okay, so universal Turing machine is really cool. And then let's talk about some initial complexity theory. So people find out the Turing machine can do really a lot of computation. So as we say here, all the reasonable computation you want to do, you can do it on Turing machine, like sorting and adding number, multiplying number, and even like running Microsoft Windows, you can write it in Turing machine. And but so the first thing people want to ask when they think about Turing machine is, can Turing machine compute everything? And yeah, and the truth on that is the answer is actually no. There is something that cannot be, I guess. Okay, so it's a little fuzzy here, but let's just say something is undecidable by a Turing machine. Okay, and I guess by decidable we mean that there is a problem that, and yeah, we'll see soon. And so I guess decidable means that there is a Turing machine that will compute the problem and stop. Okay. So the problem has some answer 0. It's actually a 0-1 problem. So the problem will so decidable by Turing machine means when the answer is 0, it will output 0 and stop. And when the answer is 1, it will output 1 and stop. Okay. But actually there is this halting problem that's not decidable by Turing machine. Okay. And I guess we will go through really quickly. And this thing is actually a bit logical. So we are trying to construct a contradictory logical system in our Turing machine. Okay. And anyway, so the halting problem is this. It's something that's pretty natural to us your Turing machine. Okay. And so it's like you ask whether your Turing machine, whether some Turing machine X will hold some input Y or loop forever. Okay. So I guess yeah. So there's something that we didn't talk too much about Turing machine, but yeah. So something you see here is so Turing machine will hold specific on a specific finite state head read set, right? And so we will hold when particular state and read when you see, and it's possible that your Turing machine just never hold. So say your Turing machine is whatever I see, I just move right, and then your Turing machine will never hold because there is no holding instruction inside. Okay. And yeah, so your Turing machine can particular input can either hold or it can either run forever. And so one question you ask is, okay, so can I decide whether some particular Turing machine and the Turing machine, as we say, can be labeled by Turing number X, holds some input Y. Yeah. Okay, so it's pretty natural to ask. And it turns out this question is undecidable. So there is no Turing machine that can solve this for every XY pair. Okay. and then we're finishing 50 minutes, so let's maybe go to proof detail. Okay, I think it's okay. Yeah. So let's go over very soon about how we prove that this is undecidable by any Turing machine. Okay. And so we go to easier problem. So problem prime, that's just a subset of this problem. So here we have x, y, and then problem prime is just we say that the Turing machine number x holds itself as an input. So we're just equating x and y. And obviously, problem prime is easier than problem because it's just the same problem with a restriction on your input. Okay. So yeah, it's a bit funny. So because yeah, so we are asking a Turing machine, and if you put its Turing number on the input itself, does it hold? Okay. And yeah, it's easier. Okay. And we can define. Okay. So this is just really a simplification of notation because we don't want to write two numbers here. Only need one to prove contradiction. Okay. And yeah, so this halting x is defined as 0 if this thing holds on itself, and it's 0 if it does not hold, and 1 if it does hold on itself. Okay. So we can define this h of x. Okay. And then we have a theorem saying that no Turing machine can compute h of x for x. And to do this, we construct a really bad Turing machine that you cannot really say really it holds or not. Okay? And so we prove a contradiction. So suppose there is a Turing machine that computes h of x. And the Turing machine is called hold. Okay. Okay, so it's very powerful. Hold can compute h of x. So we put the x inside hold of x, it will compute h of x. And then we construct a very funny Turing machine Turing from this hold. And then we will see that Turing, the h of Turing is is something that you'll define. Okay. So Turing do this. Okay, so you can also input something and maybe a halting number, so probably a Turing number. Okay, so Turing x, you will have input x, and as we say, we'll construct from hold, and so we will call hold. Okay. And so first you will compute hold x, and yeah, as we say, we okay. And yeah, I guess here we cheat a little while written this in pseudocode, and but we have been talking about Turing machine in those head and progressing. But yeah, so we cheat a little, and basically we argue here that the Turing machine can simulate a reasonable computational model, so it can also be written as pseudocode. Okay, but anyway. So we are trying to say there is no reasonable pseudocode that can solve the holding problem. And so, okay, and back to the Turing construction. So Turing x first equal the hold of x and recall the number as y. Okay, and then you do this contradictory reversing. Okay. So if y equals 0, then the Turing, then this program hold, and else then you will loop forever. Okay. So if y equals 1, you will loop forever. Okay. So you see it has two different states, either hold or loop forever. Okay. Okay, so we have a lot of recursion here, but here now we go to the contradictory part. The contradictory part is now the Turing is a Turing machine. Then it has a Turing number t, and then consider whether you put t inside itself, it holds. So we want to see what's the hold of t. Does it? If we put t inside here, does it hold? Okay. Okay. And so we prove that it's neither 0 or 1. Okay. So if h of t equal to 1, and so as we said, h of t equal to 1 means t hold on itself. So we put t inside and it hold. And if it hold, then well, it must come out here, right? It hold, then it come from here. And okay, and we go back. It hold come from here, and it means y equals 0. Y equals 0 means hold of h equals 0, but hold of t equals 0. But hold of t, yeah, and that's h of t, and so that means h of t equals 0. But we say h of t equals 1, so that's not possible. And then what if h of t equals 0? That means Turing t loop forever. Then it's the same argument. So then you must come from here, and then you go back, you see that y equals 1 means h of t equals 1. So that's also a contradiction. And yeah, so h of t cannot be 0 and it cannot be 1, and yeah, so contradiction. So we go to the conclusion that this Holt machine or this Holt algorithm doesn't really exist. Yeah. So that's the well, really quick. Yeah. So that's ancient computational theory where people find out that some problems are undecidable. And yeah, in our course, most of the problems are decidable. And later we'll see that nowadays people care about different notions. People care about the efficiency of computation. In ancient times, people think everything computed by your computer can be done really quickly because the machine do it. But nowadays, you know that the computational complexity is really hard. Some problem takes really long to compute, so people care more about compute efficiency than whether you can compute your problem. Yeah. Any question? Otherwise, then let's keep going. Yeah, let's go really quick. Okay, so that's about Turing machine, and then I'll go to our more physical and probably more practical model. That's the circuit model. So this looks like more like the computer using your head. So you have a circuit, and circuits are composed of wires and gates. So wires are those straight line, and the gates are those plugs. And so we think about wires, so maybe like physical copper wires, and they will carry information. So you will put like a 0, 1 inside your wire, and then you will carry through, and then you will hit your gate, and the gate will do computation. So the gate will have some input wire, and it will have some output wire. And the gate will have some truth table, and it will say the input is something, it will output something, and then it will pass it along and say input is something, output is something. So for example, here input 0, 0, 0, and this gate will say the output 1. And then here this gate see the input is 1, 0, and say we want to output 0, 1, 0, etc. And then when we write this, time usually go from left to right. Okay? So we think the left side is input and goes to right, and these things are the output. Okay? So this is a circuit model, and some spoiler ahead, we are also going to think a quantum computer in circuit model. Okay, and let's say a little more about gate. Okay, so the gate will do computation, and for example, there is a NOT gate that will flip a bit. So input is 0, you will get output 1, and input is 1, you will output 0. Okay, and I'll say satisfy a truth table. And then we see that we can piece different gates together as an algorithm. So we'll have some input, and the input return out a bit string. So like x1 to xn, and you will place your gate carefully, and then you will get some output f of x here. Okay. And yeah, here we get some example of gate set that hopefully everyone know. So AND gate is 2 input, 1 output. So you will compute the AND of 2 bit. So that means it's 1 if only if 2 bits are both 1. And we have OR gate. The computer or 2 bit, and that means it's 0 if only if input are both 0. And yeah, and we also have some logical notation for AND and OR. And then we have XOR. XOR is going to see a bit more in quantum computation, so let's be more careful. Okay, so it's usually written in this notation. So yeah, it's like a plus. So we'll return the XOR of 2 bit x1, x2 in this notation is plus circle. And yeah, so it means you are adding 2 bit and mod2. Okay. And so adding 2 bit mod2 means that if it's 0, 0 and 1 or 1, 1 as input, you get 0, and 1, 0 and 0, 1, you get 1. Okay. This we'll see more in quantum computation. And so yeah, so better remember XOR. And there is a NOT gate. And as we say, flip 0 and 1, and when you want to write a number, then that's just 1 minus x mod 2. And yeah, and in logical notation is a weird symbol, is weird negation symbol of x. And sometimes the people also written this ice bar. And finally there is this NAND gate. It's just really just the NOT gate and the AND gate composed together. So it's once again it's a 2 to 1 gate, and is you compute the end of x1, x2, and then you compute the NOT of it. Yeah. And people like to talk about this because it's a universal gate. Although we haven't said about what's universal. But anyway, so that's back to circuit model. We have a wire and a gate, and we have some example of gate, and something more about wires. Okay. And first thing is we don't allow feedback loop. Although physically you can kind of build this kind of system where you fork your wire and back to some previous gate, and you have a loop here. And well, depends on how you design a system. So if you want to know, you can study system signal and see whether it is stable. But a lot of times it gives you unstable system, and so you don't want to build this. And also this is not possible. Yeah. Okay. So yeah. Anyway, so we don't allow this in our classical circuit. And but something is allowed in classical but not allowed in quantum is fan out. So you can have one wire and split into 2 wire. So if this wire carries on x, then both of the wire will carry x. So if it's 0, then it's 0, 0, and if it's 1, and it's 1, 1. Okay? So fan out is allowed for classical circuit, but we try to not do this because it's not going to be allowed in quantum because there is no cloning theorem. So yeah, so you have some state side here, you can just clone it to side side. Okay, so that's something special about quantum. And 1 minute. Okay, so let's maybe stop here. Okay. So we see 2 models of computation, Turing machine, and circuit model. And we'll see the connection between them soon next class. Okay, let's have a 10-minute break and resume later. introduction from this class. Yeah. So we go over Turing machine and circuit model. Okay, and let's start talking about. Okay, so we have random other thing here. So this concept of Boolean function, and it's really just 0, 1 function. Okay. So Boolean just means 0 and 1. So you can see the Boolean function just means the input is a 0, 1 string and the output is a single 0, 1. And we justify that. So we will focus a lot of our studying to Boolean function. And so we justify this in 2 steps. So first is we say any function G is can be written as a 0, 1 string to another 0, 1 string. Because we already only care about discrete things in computer science. Okay, and if we consider our general function is 0, 1 string to 0, 1 string, and then this can be just written as m different. So nb string to nb string, then this can be written as m different Boolean function. So each output bit think it as a Boolean function. So in some sense, if you know Boolean function, then you can construct any function from them, or any discrete function. Okay, and then let's back to a little more about circuit model. And okay, I guess this is a little okay. So this concept is a little connected to universal gate set, and universal gate set is saying that we can construct any Boolean function here. In the circuit model from some finite number of gates. Okay. And for example, NOT gate, AND gate, and XOR gate, okay. And fan out. And actually you can get even smaller set, and then NOT, and or just even not NAND gate is enough. Okay. So yeah, so this is one of the reasons people like NAND gate a lot, is because it's universal for classical computation in circuit model. Okay. And yeah, by universal I mean that you can specify any algorithm by describing where to fan out and how you connect your AND gate, NOT gate, and XOR gate. Okay. Okay, so that's circuit model. And circuit model has some connection to the Turing machine. Actually, it must have connection to Turing machine because of its concern about unit circuit family. Okay, and so one thing that you might notice about circuit model is that every circuit has a fixed input size, right? So for example, the circuit here is really just have 1, 2, 3, 4. It has a 4-bit input and maybe 1-bit output. If it's Boolean function, it's 1-bit output. Yeah. And anyway, so one circuit is a fixed size. But as we say from when we discuss Turing machine, in the algorithm should really deal with the symptotic. So we should really deal with like infinite input size. So you should think about the input should not be just a fixed 4-bit. It should be 4, 6, 7, 8, 9, 10. It should be like go infinite. And but you found out that if you have different input size, then you need to draw different circuit weight because you need more wires and probably more gates. Okay, and yeah, so we think about algorithm is really deal with any input size, then yeah, then we need the circuit family. Okay, so instead of just one circuit. So we have infinite number of different input size, so we have just have infinite number of the circuit to deal with different input size. And so we have a circuit family. So algorithm is really in circuit model is a circuit family. So you have a C1 for 1-bit input, C2 for 2-bit input, all the way to infinite. Okay. Okay. So does that solve everything? Not quite yet. Okay. That's because you can cheat. So if you think about circuit family like this, and so there is a lot of information to describe this circuit family, and in particular you might cheat by hard coding your answers in the description of the circuit. For example, like you can hard code for every CN, you can hard code holding numbers inside your circuit, and then your circuit family will solve the holding problem. But we say the holding problem is unsolvable, so how is this possible? Yeah, yeah, and yeah. And so this is a more extreme example that philosophically a little weird. But in general, this hard coding is a really big problem. So you might be thinking that there are easier problems, but but you can skip the computation by just having your circuit just look up some truth table of your answers. Yeah, so last bit, we don't want our circuit to just look up tables. And so to deal with this, that's why we need Turing machine. So actually, circuit model, when you want to describe the algorithm in circuit model, you need a Turing machine. So you want to require the CN to be output by a Turing machine. So there is some Turing machine, and you will input n to the Turing machine. You will have input n into the Turing machine, and you will output the description of this CN. Okay. And yeah, so if your CN can be output this way, then it's called a uniform circuit family. And then this thing will not have a computational power more powerful than Turing machine, etc. Yeah. And yeah, so this is a bit of concern that sometimes encounter theoretically, but I believe in this course we will not really see this. Yeah. And yeah, so most of the time the circuit you think about, so say if you can write your circuit in pseudocode like this, then yeah, then it's controllable, then it's uniform, etc. And yeah, so in practice usually it is you usually got your algorithm is usually uniform, so you don't need to don't need to pay too much attention about this as long as your algorithm is as long as it's reasonable. So really it's non-uniform only when you treat like hard coding answers. Okay. And yeah, but it's a concept of a uniform circuit family. So any question? Otherwise, okay, then let's go to the part that the most computational part of this chapter, and that's the big O notation. So this will actually be in your homework and in your exam, and you need to remember what this is all about. Okay. And as we keep saying, we want to study how phase things grows, asymptotics. Okay. And a precise way to describe how things goes is this big O notation. Okay. And so here we have big O here, because the big O is the one people mostly use, but there are actually 5 of those notations. So there is big O, small O, big omega, small omega. Okay, so it's like W but actually omega, and this big theta. Okay. And okay, so it's written in this way like f of n equal to big O of g of n, or f of n equal to small n of g of n. And so this f of n and g of n is some function of n, and we want to study how fast they scale with n. So we want to see how they grow as n go to infinity. And so roughly f of n equal to big O g of n means f is less than or equal to g as n goes to infinity. And this is f is less than g. So this means those two means that g is the upper bound of f. And then we have omega. So f equal to omega of g means f is greater or equal to g, and roughly means f is greater or equal to g, and f equal to small omega of g means f is greater to g. And finally we have theta means that f is roughly equal to g. Okay. And but here those equal or greater or equal all means that we are dropping constant. Okay. So let's go to more specific definition. Okay. And here we have the syntax. Here we assume everything is positive, makes things easier. So f is positive, is positive, g is positive. Okay, And the first one, the most common one is f is order g. And the kind of mean like this. So we want to study how f grows, how the n goes to infinity, f grows and g grows. And we want to say, so maybe on a smaller part, like do whatever, but we want to study a symplectic, and we want to say, after they pay some n naught, then there exists some c such that f is less than 2, f is less than c times g. Yeah. So some schematic example is this. So for n bigger than your cutoff n naught, then f is less than this constant times g of n. Okay. And for example, your f is, I guess, 2n plus 1, right? 2n plus 1, and then we say it's order n. So usually g will want a simple function, so maybe a really usual time monomial, etc. And so here then we can have like so 2n plus 1 versus n, then we can have like where n is n equal to 1 and like c equal to 3, right? So so you can see that when n is greater or equal to 1, then it's 3, n is bigger than 2n plus 1, etc. Okay, so you see that 2n plus 1 is order n. And then the next one is f of n is small n of g. And this means that for all c, okay, so this is really different. So the first one is exists some constant is less than this c times g. And this means for all c, and in particular, this like c can be arbitrarily close to 0. Okay. And so for all c, there exists an n naught, and this n naught can be dependent on c. So that for n bigger than n naught, f n less than c times n. So here we have an example of, so n is small of n squared. Okay. And yeah. So we want to solve what is n naught, right? So we given some c, and then want n is equal to c n squared, and so that's if only if so n is positive, and that means when n is greater or equal to 1 over c, so you can pick n naught as 1 over c, and you see that whenever n is greater or equal to 1 over c, and you have this. It's not equal, right? So let's do this. Yeah. And it's the okay. Let's write this better. So n less than c times n squared, and so then you cancel this n with this n and move things to this side, and so you see the n greater than 1 over c, then you have this. Okay. So for every c you can find a naught such that these two exist. These two is satisfied. Yeah. And yeah, and intuitively you can feel this because, like in calculus, you know n squared grows faster than n, so this will happen. Okay. And yeah, okay. Okay. Yeah, and then we have two things that are the other way around. So big omega and small omega are basically the same thing, but big omega is less equal to, we have greater equal to. So g is really a low bound of f, and then small omega is similar. Okay. Okay. And one thing to say here is, so this small o and small omega, you might think is pretty weird, right? Because when you want to give upper bound and lower bound, maybe you want something tighter, right? So you want to bound this 2n plus 1 with n, and maybe this 2n plus 1, you also want to lower bound with n. Yeah. And yeah, so you can also have 2n plus 1 and here. And yeah, so you see this 2n plus 1, n and n squared is really arbitrary. So anyway, so when do you want to use the small o and small omega is usually you want to use them for like small of constant, so you write small of 1. Okay, and yeah, so for example, your f of n is small of 1, it means it's smaller than any constant. So say your f of n might be equal to like 1 over log n, and you know as n go to infinity is equal to 0, so it's smaller than 1. Okay. And yeah, then you also sometimes you will have like omega of 1, and it means that it's more than a constant. So maybe it's something really small, but it still goes to infinity. Okay. And yeah, so that's 4 of the 5 then, and finally we have the big theta. And big theta is really just satisfied by both big O and the big omega, and it means that when they go to infinity, and yeah, when f of g when n goes to infinity, f is bounded between some constant of g. Okay, so yeah, that's the definition of that. Any question? And if not, then let's slow. But anyway, let's go to some cheat sheet about about this. Okay, so we have like a very technical definition here, but actually when we try to determine the big O and the big omegas kind of stuff, or the big theta kind of stuff, you can just do by eyeball by knowing this relationship. Okay, and okay. Yeah, so there are really 4 categories that you know how they go to infinity, which one is bigger. Okay. And that the constant is less than log of x, and log of x is less than any polynomial of x, and any polynomial of x is less than exponential of x. And so if you remember in calculus you have those kind of equations. So limit x goes to 0, 1 over log x is obviously equal to 1. Limit x goes to 0, log x divided by x is equal to 0, and so it means log x is smaller than x. And I guess it's for any constant c here, so even c is 0.1. Oh, I use n, so yeah, so maybe let's use c here. Use red. Okay. Yeah, so for any constant c here, is equal to 0. And also as x goes to infinity, x of c and divide by 2 to the infinity is 0. Okay. And I guess here we should have something extra here, and also limit. Also inside this polynomial, we also have linear limit x goes to infinity, xa over xb equal to 0 if a less than b. Right. So if the power is bigger, then power is smaller, then it grows slower. Okay. So yeah, so you can really just use those and eyeball a lot of example. Okay. And for example, so n squared, then we know the 2 is less than 3, and from this limit equation, we know n squared is big O of n cubed, because yeah, so when you refresh your calculus and you think about how this limit is defined, and you see that's a stricter definition of this thing. Okay. So yeah, and yeah, I didn't write limit here because I didn't write a limit here, so something else is because the limit. This is you are inclined to write like a limit of f divided by g equal to c, kind of like this, but that's equal to c. But the trouble is this limit might not exist. So if the limit exists, then it satisfies this, but sometimes the limit not exist. So this is a bit funny here. Okay. Yeah, here they only need to have this upper bound, and the limit doesn't need to exist because the f might be oscillatory. Okay. Okay, and yeah. So, but Anyway, so that's limit things that hopefully you remember from calculus, and from those then you can see a lot of things. So like n squared is a big O of n cubed because 2 is less than 1, and as we said, is 1 over n. As n goes to infinity, is approaching 0, so it's big O of 1. It's less than any constant. And n cubed is bigger than n squared, so n squared is the lower bound of n cubed. And then you have a polynomial like 2n squared plus n. Then you can find a big theta really easy. You just find the highest order. So it's just theta of n squared. And also, as we say, exponential is bigger than any polynomial. So you have this n to the 1000 is still big O of 2 to the n. Okay. And yeah. So in practice, so in practice, this n to the 1000 might be something really big. But in theory, we will say anything in polynomial as efficient. Okay. So if you have n to the 1000, we say it's efficient. Although we haven't talked about computational complexity, so we haven't said what thing is n to the 1000. But anyway, that's the big no or notation. Any question? No? Okay, people all know this, and you remember your calculus. Okay. And yeah, really, hopefully it's easy enough for you. I will cheat you. And yeah, let's go to next thing. Okay, so a bigger notation, then we can describe a bit of computational complexity. Okay. And computational complexity is about how much resource you need to solve computational problem. And this how much we really thinking about symptotic. So we'll scale our problem size. Maybe it's n to infinity, and then we'll see how the resource needed grow. Okay. And yeah, this is the more modern way to study how hard the computation is. We found out that sometimes it's really hard to do some computation. Even you ask it for a machine to do it, it takes a lot of time. So you want to study how the resource scale. Okay. And anyway, so we have more definition here. Okay. And we focus on decision problems here. And decision problem really corresponding to Boolean function. And decision problem means that we want a yes/no answer. Yeah. So yes and no is 0 and 1. So that's a Boolean function. And so what's the problem is described as this way. Okay. So we describe problem as this formal language thing. So this formal language. Okay, so really in computer science area, a lot of things are called language. There is a natural language like English, Chinese, and there is a programming language like C++ or Python. But formal language is a different thing. Formal language is a subset of bit strings. Okay. Yeah. So language L is a subset of bit string of any length. Okay. Yeah. So for example, we can have a language like this. It's just every bit string that has all zeros. Okay. And then another language, the language can be finite or infinite. So maybe you have a finite language that just has a 0 and a 1, etc. Okay. Okay. So what we want to talk about this is we want to talk about decision problem, and we want to. Okay. So interesting thing here is this when describe the symptotic. So this language can, as we say, can have an infinite set, and the thing of it inside the language can have any length. Okay, and so yeah, so this really encompass your problem to any size, and then you can say a decision problem L is you given some x in 0, 1 start, and then you want to decide whether x is inside your language or x not inside your language. So you see we can define the decision problem of any size by just specifying this language L by this language L. Yeah. For example, you can have a decision problem to relate to this L1, and that just whether your bit string is O0. Okay. So you see the x of 0, 0 is in L1, and x of 0, 1 is not in L1. Okay. And yeah, so you see there is this one-to-one correspondence between a language and a decision problem. Once again, this language is a subset of bit string of any length. Okay. And then you can have a harder example where your language is every prime number. So it's 0, 1, which corresponds to 2, and 1, 1 is 3, and 1, 0, 1 is 5, and 1, 1, 1 is 7. Okay. And then this will ask you, this language will ask you whether input string is a prime number. Okay? Okay. So yeah. So computational complexity. So before we talk about resource, we talk about what's a computational problem. Computational problem is you want to decide whether language is a language is inside. A bit string is inside a language, and yeah. But this is really just another way to write a Boolean function, right? But I guess the difference is when you write a function has a fixed input size, right? So a function you usually have like a fixed size input domain, so like 0, 1 to the n to 0, 1. And so you have this fixed in here. But so formal language you can have arbitrary input size. Okay? But it's really similar to Boolean function. Okay, and anyway, so let's get back to the resource part of computational theory. Okay, so what's a resource for we care about? There are lots of different resources, but two most basic one is time and space. And time, is a pretty real life example you think about you do computation, right? So how long your computer will run to solve your simulation or whatever. Okay. So yeah, time you can think about is you want to solve a problem on your computer, how long it will run, how long it takes. And but instead, in terms of our circuit model and Turing machine, time means that in circuit model it means the number of gates in your circuit required. So how many gates you need to put in your circuit to solve to have your algorithm solve the problem correctly. And in Turing machine it means how many steps the Turing machine must run. So how many program steps it need to run to solve the problem. Hold and solve the problem. And then there is space. Space is also a pretty good concern. So it means in your computer, it means how many RAM and disk size you need to have on your computer to solve your problem. And so instead of a circuit, it means how many wires you need to put in your circuit to solve the problem. And and I guess in classical it's a bit funny, but basically means how many branching you need to do to solve the problem. And anyway, in Turing machine it means how many tape block actually used in your Turing machine to solve the problem. Okay, so there is time and space, and there is complexity class. Okay, so complexity class is a set of language, so basically a set of problems, and that's what we think about as hard as each other, because we want to classify whether a language or whether a language is hard or easy. Okay. And then we have this famous complexity class P, and it's polynomial time. So it's a set of language that can be solved in polynomial time. So time order n to the k for some constant k. So here you see we use a big O notation, means it's less than n to the k. And n is length of x. Yeah, n is the length of the input x. Yeah, so that's the P class. Oh, okay. And also this big O notation here. So something I forgot to say in big O, so let's go back a little. So as we say, as you probably see from the name here, so big O is the most common way people say about things. But sometimes people, but as we see here, big O means upper bound. So O is the upper bound of f. And but sometimes when people say big O, they actually mean big theta. So, yeah. So for example, this thing, the 2n squared plus n, we say it's big theta of n squared, means it's scale as n squared. And but sometimes people will write this as big O n squared, which is correct, but not quite sufficient because big theta is a big O and a big omega. Okay. So yeah, be a little careful when you write things. But anyway, here we are using the correct because it's upper bound. As long as you can solve it in this time, you can solve it in maybe even trivial time, we still think it's in P. Yeah. So P means can solve in polynomial time. And for our series, we consider P as efficient. So those are easy, efficient, solvable. Yeah. And usually this is a pretty good approximation in practice. Although, as we say, okay, so this is back to our n to the 1000 example. Okay. So if this k is 1000 and your problem can be solved in n to the 1000, it's still in P, but in practice it might be not very efficient because your exponent is too large here. But anyway, for series it is efficient, and usually in practice you can find more efficient algorithm than this. Okay. Yeah. And then there is some notation thing. So sometimes we will abuse the notation and say algorithm is in P. Okay. And so this is a really subtle thing. Okay. Because we define the P as a class of problems, right? And the problems and the algorithms are different. Okay. So really, if you are really picky about how you say things, then only problems or languages can be in P. And so it's not quite correct to say the algorithm is in P. But it's pretty clear what you mean when you say algorithm in P. And what you should say is the algorithm run in polynomial time. Okay. So yeah, that's something. And the good thing about P is it's equivalent in multiple computational model. Okay. And here we really didn't show this, but yeah, something nice to remember. Okay. And so that's P, and maybe the most famous complex class is this NP. Okay. And it stands for non-deterministic polynomial type. Okay. And non-deterministic part is really weird. is something we won't talk about. But informally, NP, okay, so it's not. But anyway, the important thing here is N doesn't stand for not. Okay. It stands for this weird non-deterministic. And the definition of NP is a set of language. And once again, languages are problems, Boolean problems. And that can be efficiently verified. And efficiently, once again, means polynomial time. Okay. So yeah, so we didn't really say how long does it take to solve the problem. But we say once you have an answer, then you can efficiently verify the answer. Okay. Kind of. And formally, language L is NP. If there is a verifying algorithm, so there is a polynomial time Turing machine. Okay. And yeah, it can be polynomial time Turing machine, but really, as we said, it's a polynomial is equivalent in multiple computational model. So really, circuit model and the Turing machine is not too different, but it's easier to write definition in Turing machine. Anyway, back to NP. So in NP, if there is a polynomial time algorithm or Turing machine, such that so really only verify when you are in the yes instance. So if it's bit string x is inside a language, then there exists some witness w, such that okay, so we have some interesting concept of witness here. So there is a witness that can verify that x is inside L. Okay, so if x is L, then you can put this w inside together with your x input x to the verifying machine. Okay, and the verifying machine will say, okay, yes, this x is really something you should accept. Okay, and the other way around is, but if x is not inside L, then you cannot trick the machine to accept. Okay, so whatever string w you feed into the machine along with x, this verifier will reject. Okay, so this is P. So if you are x in L, then there is something that you can prove some, you can supply your verifying machine with some proof along with the input to prove that your x is actually inside your language. And this machine must run efficiently. Okay. Yeah. And something funny about NP is that this is not symmetric. So, so you see that x in L, you have some witness that make the machine accept. But when x not equal L, there is nothing to verify that x is not equal L. Okay. And so we swap the in L and not L, then we get another complex class, and it's called co-NP. And people doesn't know whether co-NP equal to NP. So that's interesting. And also, so the question you might have is, well, why is NP not equal to P? So you can just try to find a witness, and then you can decide in polynomial time whether x is inside L. And the trick here is there are many possible witnesses, and to find the correct witness for your x can be really hard. Okay. So the witness can be hard to find. So here is the example, that's factoring. The decision version of factoring. Basically, you want to give a number m, and we get a natural number m, and we want to say, is it a prime? So can you factor into some number p times another number q? Okay. And but in the decision version, so we give a decision version of this because we have been saying everything decision problem. And so decision version is a bit funny. So we are given the integer m that we want to factor, and we give some cutoff L, and we want to say where is a p that's less than factor p that's less than L. So it will become a decision problem. Okay, and yeah. Okay, and so what's a witness for factoring is you have some factor p here. Okay. So if you have some, you really actually factor this n to some p smaller L, and then it's easy to check that your p is smaller than L, and then you can just do division of n with p and find out that q is integer. Yeah. So this w is really one of the factor p here. Okay. And yeah. So here is the example of NP. So factoring, you have an integer, and because division is easy to do, and so if you are given a factor, a possible factor w or p, then you can easily check that where n divided by w is an integer. And but if you are not given this w, then you need to try every p, let's say m, and there are a lot of things to try, and yeah, and that might be really hard. At least we don't know how to efficiently solve this. And some side note here is so factoring we think is not in P, but actually testing whether something is prime is in P. So that's just some digression. And so now we talk a little thing about complexity class. So we start drawing this weird diagram. So once again, remember the P and NP, they are set of languages. Okay? So they are set of problems that we think that about how does each other, or okay, so that's a weird thing. That's like easier, that's hard to some extent. Okay? And so complexity series want to like to study like the relationship between different complexity classes. And very easy thing to prove is P is inside NP. So that means if language is in P, and then it's actually also in NP. So it's easy to prove. So you just say that if you can solve the problem in polynomial time, then you can also verify it in polynomial time. So because you really don't need witness here, so you just have your verifier run the whatever algorithm solve your P problem, and the answer will verify whether it's yes or no. Okay, so P in NP is trivial, but whether P not equal to NP, whether P not equal to NP, then it's a question that a lot of people spend a lot of time to study. Okay. So if so this problem really means that is there something between NP and P? So is there some problem that's easy to verify but hard to actually compute? Okay. So that's one of the central problems in computer science. And also, as we said, there is a co-NP where you flip the yes and no in P, and it's actually a different problem. Okay. And okay, so drawing here is a bit wrong. Yeah. So when you draw P and co-NP and P, and so really there are different set of problems, and they have some intersection, and P is inside the intersection. But really we don't know whether each of these parts have we don't know whether there are things inside this part where there is something in NP and not equal to P, or there is something equal to P not equal to P, because we don't even know whether NP equal to P. Okay. Although, okay, and we have a little more time. Okay. Okay, let's see whether we can finish this in 7 minutes. Okay, now we talk about important concept, that's reduction. Actually, this is, I guess we don't really have homework on this, but this is a really important concept. Okay. And so let's say you can reduce the problem to each other. This is something that you do a lot in actual programming, right? So basically you want to solve a problem by kind of divide and conquer. So you have a hard problem, then you will solve an easier problem. You will cut it into a smaller part and solve the easier problem first. Okay. And so anyway, so let's do this more formally. So we have A, B, two language, and we will sometimes say A reduced to B. Means that we can solve A efficiently, we can solve B efficiently. We can. Or okay, that's a weird way to say. But basically it means that we can solve A, we can solve B. And with a polynomial overhead. So we can solve B in some time, then we can solve A in the similar time with times some polynomial. Okay. And the idea is that you can construct an algorithm of A by having B as a sub-algorithm. Okay. So this is kind of divide and conquer. You separate out some special part of your problem, and you solve it with another algorithm, and then your total algorithm will keep calling this algorithm a B. Okay. And but although B is a sub-algorithm, but So okay, so this is kind of counterintuitive because you see B is a smaller part, but actually B is harder because B might solve a more general problem than algorithm for A. Okay, because yeah, because if you can solve B, then you can solve A. Then so B is actually a problem. Is actually harder. Okay, in terms of complexity theory. This is a little counterintuitive to this algorithm view, but yeah, this is correct. And okay, but this view hides a little detail. So actually there are two types of reduction, and this is theoretical, but it's nice to know the difference. So there's cup reduction versus Cook reduction, and cup reduction is okay. Okay. Yeah. I guess it's better to say Cook reduction first. So this view here is the Cook reduction. So it means there is algorithm for B, then you have algorithm for A that calls your algorithm for B as a sub-algorithm. Okay. And you might call this polynomial type. And the cup reduction is a more mathematical thing. And so it means that there is a one-to-one correspondence that you can map an instance in A to an instance in B. Okay. So remember, we want to say, okay, so A and B are languages, okay, and the thing we want to see, the thing we want to solve for a language is whether your input string X is inside your language, okay. And the cup reduction is saying that you can just map this input to a different input of X efficiently. Okay. And so if you want to solve whether X inside A, then you want to just solve whether f of X inside B. Okay. So if you can solve this, then you can map. So yeah, so if you want to solve this, then you compute f of X efficiently, then you just solve on this B part. And yeah, and this should happen for every X. So this is a really mathematical mapping between this problem A and problem B. And basically, when you think about this sub-algorithm view, this means that you want to solve this problem of A, then you only need to solve a problem of B once, because you do the mapping, then you just solve this once. Whereas in this Cook reduction, you can call algorithm B many times. Okay, any question? Okay, then finally we can talk about complete problem, this famous NP complete. And NP complete problem means the hardest problem of a class. And by hardest, we mean everything can reduce to that. Remember here, this thing. B is hardest if everything about A can be reduced to it. Okay. And yeah, so we have some language L, and we say it's complete for complete class A if, so there are really two things. Okay. So L must be inside A, and L is harder than everything A, means that whatever L prime in A, L prime can be reduced to L. Okay. And so in that case, and we call L is A complete. And if you only satisfy 2, so if L is not necessary, is not inside A, not necessary inside A, then it's called A hard. Okay. And so for example, everything inside P is P complete. Okay. Because the reduction here will allow any polynomial. And then the interesting thing about this is there are NP complete problem. So there are things that are inside NP, and everything inside NP can be reduced to that. And two example is 3 coloring and 3 set. And yeah, so let's just see one of them, and you can read the other. So like 3 coloring is this problem where input is a graph with vertices and edges, and they want to see whether you can color your vertex with only 3 different possible colors or in RGB. And such that every edge has different colors on its 2 sides. Yeah, so 3 coloring. And yeah, so there exists a lot of NP complete problems, and they are famous. And they solve any one of them then efficiently, then you can solve any NP problem efficiently. Yeah. And then once you will talk about that is factoring because of the efficient quantum algorithm for it. And but unfortunately, factoring has not been proven to be NP complete. People believe that it's probably not NP complete, but as everything in complexity theory, there's people have a strong belief, but they don't really have a rigorous proof. Okay, nice, we're exactly on time. And yeah, so we finish this. So any question? Oh, sorry, a little over time, but announcement is the midterm should happen in 2 weeks. In 2 weeks, yeah, 2 weeks. And yeah, so if I go to, can you see this here? Yeah, yeah. So I believe we are on 6th week, and the midterm is scheduled on the 8th week of Thursday, so it should happen in this November 12th. Yeah. And so same class time, and, oh sorry, November 2, yeah, November 2, and class time and this location. And the range, range I'll announce later because I'm not really decided, but I think it's okay if we also include a little bit on Monday. Yeah. Yeah, so everything until now will definitely in range, but I would like to talk a little about quantum circuit and yeah. Yeah, I will decide whether we'll put some circuit inside also. And I'll make a formal announcement later. Yeah. But just let you know the schedule. Okay, if there's no question, then see you next week. Oh, yeah, next class is on Monday and Tuesday.